You're good.
I'm going to pass this over to Bernadette with the Colorado Space Grant Consortium.
I know we've been sitting a while. If you need to stand up, please stand up and, I don't know, let your butt cheeks get some blood flow. I was thinking, since we do have one team that's doing a kit payload, McKenna, were they going to do a presentation? If you all want to go ahead and come down, we'll start with you, since you're going to kind of show the kit approach. So just a quick introduction. My name is Bernadette Garcia Galvez. I'm the Deputy Director of the Colorado Space Grant Program. There is a space grant program. You heard somebody mention Montana. There's a space grant program in every state in the country, and we're funded out of NASA Office of STEM Engagement. And our purpose, do you all have slides?
Yeah, I got it.
Okay. While they're getting their slides up. Our purpose is to give post-secondary students a chance to have some practical experience. So here in the state of Colorado, we facilitate orbital space missions, suborbital missions, as well as Earth-focused research projects. EOSS, this partnership allows us to do a really exciting suborbital program throughout the entire state. So we have 19 institutions of higher education that are part of our consortium, and we have students who participate in these flights 3 times a year. So we have one in the fall, one in the spring, and it's really exciting that our summer one we get to do in conjunction with GPSL. Before you get started, I did want to just give everybody an idea of what this collaboration has meant to Space Grant. So we have had a total of 112 flight days, flying 177 balloons, 1,278 payloads, and that has engaged 5,044 students. So this is by far the biggest activity with Colorado Space Grant. So it's the one that we engage the most students, and it's a really unique opportunity to get students to build something and get the experience of having to design a payload that has to be integrated into a launch vehicle, and it's the perfect step. So the next time they do it, maybe they're designing something that's going up on a rocket, or even maybe getting into orbit. So we have some students who start the experience building kits. So we have little kits that they can actually follow some curriculum online and build a kit, and that's what this team's going to talk about. And then once they've built that kit, we have teams that build payloads from scratch. So they're participating in a design series where they're doing design reviews throughout the semester, and they're coming up with their own experiments. So you'll get to hear about some of the things. We're talking into this microphone because we have people who are participating online, and this is how we make sure they can hear us.
Oh, okay. Thank you. So we're Boys in the Air, and we did a kit for our flight. My name's Alex, and this is...
I'm Tristan Hartzell.
So honestly, it was a very simple kit to do. It's just got to go to space. Here we have some of the sensors, or all the sensors that we have, just a pressure one, humidity, 2 thermometers, one inside, one out, and then an accelerometer, but only gets X and Z data, so no Y. And it all gets recorded into an SD card.
All right, so this is the basic overview of how the kit works. So it's Velcro secured in this foam board box with an external shield and Arduino inside that has all the sensors and records all the data necessary for those conditions.
And then just to show you guys an overview of what it records, basically it records everything in a TXT file and then we put it into a CVS. And here's our temperature. Our outer one is up here, and inner one, you can see how it's kind of doesn't fluctuate as much as the outer one. Here you can see the X and the Z kind of spike together. Then our humidity and our pressure. Humidity, that sensor we were playing with, we kind of just blew onto it.
So these are kind of the conditions we're expecting on the way up. So as you see in the troposphere, temperature is going to slowly go down until you hit the tropopause, and then in the stratosphere it's going to go up, and it's going to deviate back and forth until you hit about 80 degrees in the thermosphere at its highest point.
And prediction for pressure, as long as it's going up, the pressure is going down. And it's not going to hit the exosphere, I think. So I don't think it'll reach 0 or close to 0, but it'll be close.
So humidity should decline as the payload goes higher, and it should get close to 0, if not hit 0 at some point.
And honestly, since it was a really simple project and we didn't really have that many moving parts, we think we're really confident in it being ready to go. Yeah, go for launch. Oh, and it weighs only 171 grams, and it costs $150.
Thank you. I have a question. Did y'all do any testing?
Yes. The data that we showed right there was just letting it sit while we're assembling the housing. So we tested the pressure sensor twice. Not sure why they didn't pop up. Probably didn't test it properly, but.
Okay. And did you do, once you got your system integrated into the structure, did you shake it at all or whip it around to make sure everything's going to stay put?
Yeah, we did.
Okay.
The Velcro. If you saw the little spike on the X, at the XZ one, that was from shaking it around.
Perfect. All right. Thank you.
Thank you.
Quick question, what are you using for power?
Oh, a 9-volt battery.
Just a regular 9
Yeah,
volt?
just a 9-volt. You want to look at it? You got it.
Alkaline or lithium?
Ultimate lithium or?
Which one's go
Ultimate lithium.
Okay.
Just a simple 9-volt battery.
Well, they're not simple, they're expensive.
But they're simple.
Thank you both for going first. Do we have a team who wants to go next?
All right, hello everybody. We are the CSU team. We are the Yaw Masters, and this is our flight readiness review. We were working on a self-orienting payload with reaction wheel control dynamics. My name is Zen.
I'm Thomas. I'm Kyle. And I'm Isai.
And we have a lot of content to get through, so we're going to move pretty quickly, and we're going to get started right into this.
Alrighty, here's kind of our overview. We're going to introduce our project. We're going to go over our mission overview, the design and assembly, concept of operations, and the testing that we've done. So our design was a self-orienting payload using a reaction wheel. The goal of this is to better help solar data and camera imaging. It uses an active stabilization method with the reaction wheel. If you look at the picture on the right, we have a geared system with the flywheel in the center, so the flight string could still go through the payload. What we want to do is control the flywheel by spinning it up or down, which changes the orientation of the satellite itself. We got a couple videos for you. So on the left is a bare bones, so you can see what actually is going on. And then on the right is our full-scale test. Sorry, it's just a brick wall, but you can see that it's working, holding in the same direction. So our goal is to test our onboard PID, and we're going to do two different tests, one in the troposphere and one in the stratosphere, with breaks in between, in order to hold the orientation within 35 degrees, plus or minus.
So what are the different sub-assemblies? We have three primary ones: the reaction wheel, the satellite, and the flight tube mount. So here's our satellite subassembly. Its primary goal is to integrate the flywheel attachment shaft, which is that center carbon fiber tube. It also houses the electronics and has a rigid structure which can withstand the impact. This is our reaction wheel, which we also interchangeably call the flywheel. And it uses the laws of conservation of angular momentum to create a counter torque, which is supposed to change the orientation of the whole satellite. And then this is our flight tube mount. This provides a way for the payload to attach to the flight string with bearings, allowing the payload to freely spin around it. And we found this to be particularly important, because since we have a very dynamic payload, we didn't want to interact with the flight string in a way that could compromise the flight.
So our electronics include an Arduino Mega to accommodate all the sensors that we'll be including, an encoder gear motor that's attached to the flywheel. That is driven by a motor driver to control the flywheel speed. And at the heart of our data collection is the IMU, which measures gyroscope, accelerometer, and magnetometer data. And that's where we retrieve the yaw and yaw velocity readings. We also have a wind, pressure, temperature sensor for environmental data. And we also made sure, took the step to secure our components so that they stay at operating temperatures through a heating pad. And this is all powered up by a 3,000 milliamp LiPo battery. And we'll make sure to collect all the data through a micro SD reader.
So our control model is a system of two proportional integral derivative controllers that are going to control the yaw of the payload and the yaw velocity of the payload. Our goal is to have our yaw stay in a range of plus or minus 35 degrees of the reference angle throughout the duration of our mission. So also one of the goals from this project was to develop a turbulent model to better understand how the atmosphere wind velocities affect the yaw of a weather balloon as it's going up through the atmosphere. So that's also something that we're going to do post-process. So for our embedded code in the microprocessor, we have the basic reading and processing sensor data, temperature control to keep it in the range of -10 Celsius and 1 Celsius, computing the PID, actuating the motor, logging the data, desaturating the flywheel if need be, so if we ever reach a certain RPM that's too fast, we can slow it down carefully, and then also when the balloon pops, we're going to turn off the motor so it's not going to be active in the descent phase. And then also we have software for post-process, which is just visualizing the data, doing some statistical analysis on our mission, and then estimating our turbulent model.
So this is our concept of operations. On the right, it's kind of a graphic highlighting what it's going to look like. We're going to have power on at ground level, which in Lyman is about 1.6 kilometers above sea level. We're going to do our launch preparations, and then we're going to release the balloon. After that, we're going to start 2 tests. There's going to be 2 testing periods, one in the troposphere and one in the stratosphere. The tropospheric test is going to be 7 kilometers between 3 kilometers of altitude to 10 kilometers of altitude. And the stratospheric test is going to be a 10-kilometer test between 15 and 25. In between those tests, there's going to be a resting period. This is to have data to compare to for its non-orienting and orienting modes. While the balloon's in flight, it's going to be controlling the reaction wheel. It's going to be transmitting and logging data. It'll be self-regulating temperature, and it'll be taking video. And once the balloon pops, the reaction wheel is going to slowly come to a stop to avoid affecting the flight during descent in any way.
So for our initial design, we were planning on implementing telemetry, long range, through ham radio, but we shifted our focus to just working specifically on the onboard control. We want to ensure that the payload does not interfere or possibly damage the flight stream during operation, and we did this through refining the code through tested fail-safes and rigorous testing, which we could later further explain on the slides. So for our required tests, we did a freeze, vacuum, stare, drop test, and the whip test. And we also added we added some tests for our payload to ensure that it's ready for flight. So for the freeze test, we put the payload inside a cooler with dry ice, and we let it sit for 2 hours. At the bottom of the cooler, it reached temperatures of -50 Celsius, and the air temperature was at -15 Celsius. All the electronics operated as expected, and we also have some data. While testing this, we could see the temperature decrease But once it reached that -10 Celsius, which we added on the code for the heaters to turn on, we see that rise back again. We also conducted a vacuum test at the CSU powerhouse. We wanted to test out our pressure sensor, since we're going to be recording altitude data, take the pressure readings and convert it into altitude. And we were roughly estimating for a reading of like as low as vacuum levels, approximately 2.0 torque, which is roughly where it happens at 30 kilometers. As you can see, the results on your left is the pressure versus time, and we see that decrease in pressure, and then the altitude versus time, we see that increase as pressure decreases. We also conducted a stair test to kind of simulate that the landing vibrations of the payload as it arrives back on Earth. All the electronics stayed in place. We also ensured that all the gears that we're using within our payload are intact, and made sure to secure them properly. We also did a whip test. We just attached the payload to a string and we swung it around. We noticed that the camera that we're using kind of was flying around the payload, but we fixed that by adding some glue and securing it properly.
So we also conducted a functionality test where we left our payload running for about 2 hours, giving it different PWM signals for the motor to see how our system responds. We got some really great data from this and some input for our battery size. And yeah, we also did a fair amount of simulated ascent tests where to test our whole mission in our code, we just stepped up our altitude at every time step to simulate our logic in the code throughout the mission. So this was really good to test some of the things like the balloon popping and the desaturation, because those are hard to test in real life. So we learned some great stuff about that to fix it. And also we got some results from this. These are just mainly assuring that we're not doing anything crazy with our payload. So our yaw velocity and our pitch and our roll are not doing anything extreme. This was not including wind velocities, just as a side note.
For our drop testing, we wanted to make sure it survives on the way down. So we did 2 different drop testing. We found that our initial designs had a little bit too thin of walls, so we just made them a little bit more beefier, had them thicken up. All of the parts that we have for our design are 3D printed and designed by us as a team. One of the bottom right picture was our mount for our motor and the flight tube, or the tube for the flywheel, and it broke in the same spot 2 different times. So that was one of the things that was an easy failure analysis. It's fixed and ready to go for the next test.
So this is our full-scale test. This pretty much represents the pinnacle of all of our testing. We strung out multiple payloads with simulated weights that were accurate following the EOSS balloon assembly, specifically the heavyweight one. And we had 2 goals. We wanted to see how well our payload functioned and see how our payload affected the payloads around us. The test ran with the simulated altitude to test the functionality, and we ran a separate worst-case scenario test, which we'll get into in a second. And our results of what we found is they functioned essentially exactly how we expected. There was a little bit of an effect of spinning on other payloads, but at the mounting point, specifically if this is the payload section here, where it connects to the next, I don't know if it's a payload or a radio assembly in this GPS module, they really don't rotate at all, and so we're not worried about it affecting anything aside from the payloads around it.
So to make sure we don't interfere with the flight string and ruin any flights, we did a bunch of worst case scenario tests. This video right here is the flywheel going max speed in one direction, the max speed in the opposite direction, giving it the most change in RPM for the satellite itself. We found that to be 143 RPMs. This is a worst case scenario that we also have code that will slow down the motor and stop this if this were to occur. We also have this on the full-scale test. We did a similar test where we turned it to the max speed. Both of these videos are time synced. This is at the very top of the rope. The rope we used is the fly string rope that Bernadette gave to us, that she will be tying it on. So as you can see, there's some spinning in the other payloads, but at the very top, there's no spinning at all. And then from our testing, we found that only in the worst case scenario will we ever reach that 143 RPM.
And these are our on-site launch preparations that we still have to do. We still need to calibrate the magnetometer. We are going to turn on the camera, tape the walls down, and switch the payload on and send her up. Thank you.
What's the total weight?
Our total weight is about 1,320 grams
Okay.
specifically.
Got exact amount right here,
Yep.
1321.
We'll be doing a final weigh-in before spring.
I just hear that's a lot of equipment.
Yeah.
Yeah, we jam-packed it full of stuff.
Yeah. What's your team name?
Yaw Masters under CSU DemoSat.
Okay.
Yes?
What's your flywheel consist of? How do you make your flywheel?
Yeah, that's a good question. He asked what our flywheel consists of. It's made out of a 3D printed material, and I'll show it from the side here. It's a 100% infill density. The reason we chose 3D materials is because it allowed for rapid prototyping, and it's a fairly dense material if you print it at 100%.
And what's the material? ABS
It's PLA.
PLA?
The middle is also ABS to get a lower density on the inside, increasing the moment of inertia.
Yes?
So, I'm Steve here with USS. I'm the guy you got to convince it's safe to fly.
Oh.
So I have 4 questions for you here.
Okay, we're excited.
What percentage of thickness of the walls did you change after it wasn't substantial enough?
Yep.
After our drop test, we increased all the walls by 50%, even if they didn't break. They're about 10 millimeters thick on each side and 8 millimeters, or 7 millimeters thick. So
And that's PLA?
the outside is ABS.
ABS, okay. Talk to me about your battery, and how your battery is enclosed and how it's mounted in the
We got a wall, so you can't really show you, but we can talk about it. We have foam similar to the outside that encases the battery to make sure there's nothing that can puncture it. There's also a PLA casing as well to make sure there's no sharp objects can pierce it.
Perfect. Awesome. How do you determine altitude for the different phases?
You wanna
We determine altitude through our pressure readings. Yeah, just a barometric equation.
Great. Cool. And how long is it going to take you to go from when I start talking about we're going to move from the flight line out? How long is it going to take you to get ready to launch and talking about that?
We talked to Bernadette about that. We're going to show up a little bit earlier than everybody else. That way we can get it calibrated, and then all we have to do is hit the on button on the camera and then tape that side down.
Okay, so camera, close up, go 10 minutes?
Yep.
1 minute most likely.
Okay.
10 minutes at its worst.
Yeah.
All right, and you can do all that while it's already strung?
Yep.
Yes.
Perfect. Awesome. Well done, guys. Appreciate
Thank
it.
you.
It looked like all your testing was done along the z-axis. Did you do any testing as if the wind came along and knocked it sideways?
Yes.
Yeah, so on our big functionality test, we went up to the roof, tied it, got all the right lengths, and then we swung it around a bunch. We weren't able to push the payload because it was 20 feet in the air, but we had the rope on the bottom, and we swung it. I think the max angle we could get to without hitting anything was 60 degrees.
And you had the controller on at that time?
Yep. One of the things that we found was when needing correction, the payload functions really good. There's no steady state error where it's oscillating back and forth. So we're predicting that in the flight it should operate a little better than the 35 degrees that we're aiming for.
What impact velocity correlates to 18-foot drop tests?
We did do the calculations for that, but I forgot it.
I believe it was about half of what like the maximum was listed. And later there was an accidental drop test with our whip test. It was moving pretty fast. We calculated its maximum acceleration force it was experiencing was 12 Gs, and then it hit the ground with that. So, and honestly, like in design towards the end when we were trying to optimize our time, we wanted to make sure that it would survive the drop test, but if something cracked and we ever had to reprint it in the future, that was a time sacrifice that we were willing to make.
All those unscheduled.
Yes?
I'm curious about how you decided on your PID settings, particularly the I and the D, and how did you decide where to start out, and did you modify them after testing to make sure you actually weren't introducing oscillation instead of dampening it?
Yeah, so we started out just with a P controller, and then we manually did I and D, but we also tried to do some system identification to find a model to optimally do it, which did help our initial guesses for our manual tuning of the coefficients.
Did you do any adjustment?
Yeah, so we did, it was like very iterative, so we did adjustments during and after all of the testing, yeah.
How are you determining burst altitude?
Burst
Or when
al-
burst occurs? How are you determining burst altitude?
We have a few things set up, so we'll keep track of what the altitude was 400 iterations ago. And if it's ever less than that, it will call that function. Also, if the z acceleration is a certain point, and also we have a fail-safe, just if it ever goes past a certain altitude, it will also be shut off no matter what.
So I'm assuming that question was also in regards to like how do we know when to turn everything off? Is that right?
Somewhat.
Yeah, how are we determining burst?
Yeah,
Yeah, burst
you
is
do.
either determined by it hitting 30 kilometers or it just being less than the altitude it was a couple like
Okay.
seconds ago, right?
Okay.
All right, any more questions?
Thank you, team.
Awesome, thank you very much.
Hi, we are Cool Beans. We are from Red Rocks Community College. I'm Phoenix Drake. I've been the team lead for this project.
I'm Miles McGowan.
I'm Chase Jones.
I'm AJ Diamond.
All right, and I do want to say that this is actually the third time that we've tried to fly. This is our spring-fall project from last year, and then flight got canceled 2 whole times. So we are flying that project now. Finally, I'm super excited to finally fly our experiment. So what is our experiment exactly? Well, previous demosat teams have found that when previous demosat teams have done experiments with seeds, all those seeds actually came back and grew a lot faster, which sounds like a mutation to me. So our hypothesis, our theory, is that something up there to do with the UV and other high altitude radiation is causing these plants to produce more natural levels of gibberellic acid as they grow. What the heck is gibberellic acid? Well, it's a plant growth hormone. It's naturally found in plants, though sometimes it is added in agriculture artificially, but it essentially just makes them grow faster. So we are testing to see if specifically carrot and cabbage seeds are affected by the high altitude conditions, specifically regarding the gibberellic acid mechanism.
All right, so as far as the design overview of the payload, these are going to be the standard temperature environmental sensors that we have on here that was provided to us with a kit from Colorado Space Grant. So we had 2 temperature sensors, one internal to the system, one external. We have a pressure sensor, a humidity sensor, accelerometer, and then this is all going to be recorded using the SparkFun data loader. Next slide, please. So as far as our custom environmental sensor, so to speak, we're going to have a wired UV sensor. That's going to be it's going to be the SparkFun UV sensor. It uses the AS7331 photodiode. It has 3 separate sensors, one for UVA, one for UVB, and one for UVC. So this is that picture up there. That is our UV sensor. It's wired to our logic converter. That's just because that specific UV sensor is 3.3 volts, and Arduino is based on a 5-volt system. We can't program that specific thing, that's hard embedded into the Arduino system, so we have to use that logic converter. But we did all of our testing using the logic converter in the past. Yeah, so we shouldn't run into any issues. Next slide. So this is our flight tube integration. As with all the other demo set payloads, it just goes straight through the payload system and is secured to the top using a paper clip and is reinforced with a metal washer.
So here are our drop and whip test results. So we did the standard drop test from 2 stories. And we also whipped it around above our heads. We also actually had an accidental drop test on our whip test as well. You can see it logged in the data over there. You can see where it hits the ground. But yeah, it passed. We actually ended up doing like 2 or 3 drop tests as we had a really long time to do them. So it passed all of them. We did have to reprint this nose cone here, but we only did that once, and it's much stronger now. We had to increase the thickness. So we did our cold test in a -80 freezer. So these are the relative data from that. And so as you can see, our internal temp is the top one, our external temp is the bottom one. And it stays well ahead of the external temp there for quite a while before it drops down to -80, which is colder than it should be for any length of time during the flight. But also we have our humidity sensor here, which is important because we believe that's why it eventually failed, is because there was like humidity buildup that was like freezing onto our electrical components, and it caused them to turn off and break, which shouldn't be a problem at higher altitudes because there should be less humidity as you go up there. So yeah, our bench test was pretty simple. We left it running for 4 hours, and it collected all the data, all the sensors worked. We just have a standard D battery, nothing special with it, and it ran the whole time. We did a couple of them, and it was something like 1 D battery to do 2 or 3 of these 4-hour stints, so we should have plenty of battery power, and there's no problem with the data logging or anything like that.
So as far as our predicted data, we have a few things. So obviously, since we're testing seeds, we have some data to expect with when we get the seeds on the ground and start doing tests with the seeds. We're going to monitor the seed growth with controls of just seeds from the ground and also seeds that went up in the payload, which, by the way, are in a quartz cuvette on the side that we have covered so they don't get any unwanted UV exposure before the experiment. But since we think UV is a part of it, we're exposing them to UV and testing those against controls with gibberellic acid that we also have within the payload, along with control seeds inside of the payload, not in the cuvette. So we're going to monitor that growth over a few weeks and see if some of them grow faster, some of them grow slower, and compare that to the ones where we artificially add gibberellic acid. And we'll record the lengths of the seedling sprouts, and we'll record the number of successful sprouts per bag, because we're going to use Ziploc bags with like napkins. If you remember from like 3rd grade, if you did an experiment where you put a seed in a Ziploc bag with a wet napkin, we're doing that because it's easy to see the growth, and it was the most successful out of anything we tried. So our predicted data for the actual sensors and other stuff in here, we have this exact same graph for the external temperature that we pulled from this website here, and we're just expecting, the temperature to gradually decrease as we go up through the different layers in the atmosphere. The expected internal temperature, this is from the -80 test, so this graph is ours, and obviously we see that the temperature goes down, and we're planning to mitigate that with heat with hand warmers inside. And then over here we have pressure. Obviously the atmospheric pressure is going to keep going down as we go up. And then some more predicted data, specifically this is for humidity, so we expect that to fluctuate a little bit. This is height here, and this is relative humidity. So this is higher humidity, lower humidity, and that's going to fluctuate a little bit as we increase in altitude. And over there, that is for our UV sensors. So we expect to definitely get obviously UVA and UVB, and maybe a little bit of UVC, but we probably won't get high enough to get a lot of UVC. It'll just be just a touch. So we aren't really planning to record that in our data. As far as what's left, all we have left is to do some stuff on the launch site. We still need to put the hand warmers in there and activate the hand warmers, and then we need to tape up the side because we need to get in there to do the hand warmers, turn it all on, send her up, and hopefully the UV sensors come back working because demo set teams have had a lot of issues with that in the past, but we have 4 of them. We're hoping one of them stays working. So with that, we have a go for flight.
So for the weight summary, we only clocked in around 657 grams. That's including the tape that we need to put on it at the launch site. So it might be a few grams lighter or a few grams heavier, but it's basically that number. Next slide, please. As for the cost, a lot of this was us rebuying things because originally, since our team is named Cool Beans, we bought beans. About halfway through this the process for this, we realized gibberellic acid doesn't work with beans, hence the switch to carrots and cabbage. And the first UV sensor we got was both not particularly good and had false advertising on it for where we bought it from, so it didn't act as expected, so we had to replace it.
So that's our presentation. I do want to say something on the beans, though. We have, our name is Cool Beans. We have it on our payload. So why are we lying? We're not lying. We had some beans left over, so we just, since we're way under, we put the beans in there, and when they come back, we're going to plant them, and we're going to make space chili with them. So that's our plan with the beans. Cool. And that is our presentation. Thank you.
So what's your experimental design? You'll have controls both in the package and on the ground?
Yeah, so we have carrot and cabbage seeds in the quartz cuvette on the side that we are going to expose to UV and other upper atmospheric radiation. Inside the payload, we have the same seeds along with the gibberellic acid, just to throw it up there as well, why not? We have the weight. So we're going to see if that is any different from the UV exposed, and then we also have some seeds we're leaving on the ground, and obviously a bunch of gibberellic acid that we leave on the ground. And when we plant these seeds and grow them, we're going to have some seeds from the ground, no gibberellic acid, some seeds from the ground with gibberellic acid. Same thing with the flight seeds and the flight gibberellic acid, and we're going to see if the seeds from flight with no gibberellic acid added that have been exposed to UV grow at a similar or hopefully the same rate as the ground control seeds with added gibberellic acid, so that we can see if the reason they're growing faster is because they're naturally making more of it. Yeah, front.
What was the model of SparkFun UV sensor you were using again?
I forget what the exact SparkFun model was, but I know that it's they only have 2, and they're using the same photodiode on it. It's the AS7331. We have the full size one with the 2 quick connectors on the side. The other one that's available that uses the same photodiode is the micro. It's about half the size.
So the satellite's going to be, BalloonSat's going to be spinning. Are you worried that you're not going to get enough exposure?
That's actually why it's a pyramid. So if you notice, most of the demostat payloads, they're square. We decided to make it a pyramid. That's not just because I think that pyramids are cooler than squares, but that's also because we thought that a pyramid, just because of the way it's shaped, if we have a UV sensor on one side, that's going to get the most even possible UV exposure. Because if you have light, it's mostly, hopefully, going to evenly spread from the different sides out of all the shapes we could have picked. So we're a little tiny bit worried about it just because it's so small, but I think that the seeds at least will get enough UV exposure. And the UV data isn't as important as the seed data themselves, and since the seeds have a bigger opening, I'm not worried about them.
Well, you'll find out if you start seeing a lot of oscillation on your UV sensor.
Yeah, for sure.
Which could be due to spinning.
I have a question for Bernadette. Weight. Remember in the past we've had trouble with people adding weight after they were, and they're talking about adding the heating elements and taping.
Yeah.
Are you taking care of that problem before we fill to the proper correct weight?
Yeah, so if you go back to the weight slide, you'll see that we actually did weigh all of those and include them in our total weight summary already, including the tape and the hand warmers in there. They're just not like activated right now, but we put them on the scale with them, and we added, we have the tape that we're going to be using, we put it in there. So our total down there is correct for what's going to be on there. We're not adding anything extra that's unweighed.
Front.
Oh, I had a copy, a comment about the proper weights. You're very detailed, and I appreciate that, because I worked with a school once that when I turned my back, they stuck an extra payload on I wasn't aware of.
No, we didn't do that, promise.
And when it went up, we were in Birmingham, Alabama, 700 miles from the ocean. It goes up with 2 ounces of free lift instead of 2 pounds. It took 7 hours to get to altitude and ended up 700 miles downrange in the Atlantic Ocean. And all those cameras and all the sensors, everything flashed down 100 miles out to sea.
Yeah, this is as correct as can be. The only extra thing we added is the assorted beans, which are included, so.
I'll borrow this real quick. Also, so our practice is students always do report their weights because we want them to be tracking that. But as they hand it to me, I am the one integrating it onto the flight string. We have a scale right there. They place it on the scale, we record their weight, and it never leaves my sight. So that has not happened to us yet, but who knows? I suppose that could always happen, but I think we have it controlled pretty well.
Yeah, front.
You have a test called -80. I don't know what that means, and the graphs that you're showing are not hitting -80. So can you explain that to me?
Yes, that's because our electronics failed before it got to -80. So it's just a -80 freezer, which is what we use for storing like bacterial samples and stuff, which our schools happen to have in our bio lab. So we just put it in there for, do you remember, I think it was an hour or two? 2 hours. And it got down to -80, but our electronics failed before it hit -80. I think we made it down to roughly -50. I think it was a little below that, but it did some weird recording things when it was breaking, so some of the data didn't get properly logged, and it was in like different files.
Is that Celsius?
It's in Celsius.
Yes, Celsius, yeah.
Why did you start at 100?
That is a good question.
That's because the hand warmers were activated beforehand.
Yes. So we have to start our hand warmers before we put it in, so it does get pretty warm in there, although it shouldn't get too warm because it burns up oxygen as it's doing it, and as it's sitting still, there's not a lot of oxygen coming in, so it should like curb the reaction, but then as it starts moving again, it'll get air forced through it, bringing the temperature back up, keeping it warm as it goes. And it was just, as for why the external temperature is so high, it was just like a warm day when we were doing it. But yeah, the only reason we believe it failed during this test is because it was pretty humid inside the -80, so all the humidity froze onto our board, which ended up like causing it to stop working. But as it is going up in the atmosphere, it should have way less humidity than down here on the ground. So we're not expecting that problem again.
You mentioned it got really hot inside, and I agree. I've had payloads fail just from sitting in the sun while we're waiting to launch. And I'm concerned, even if your electronics survive, are your seeds going to survive being exposed to that high temperature if it's sitting on the flight string for half an hour before we get it in the air?
They should. So we have the seed. We can't open it because we have it kind of taped shut just so nothing falls out before tomorrow and it can survive transport. But we have all of the seeds on the bottom, and none of the hand warmers are going to be touching those seeds. So I'm not too worried about it since seeds already endure pretty extreme temperatures. So that shouldn't inhibit their growth, and especially for the ones in the cuvette, since they're more outside the payload, those should especially be fine, and that's our main test. So. Yeah, in the back.
More questions, please. What is the green thing on the hot mid now?
PLA.
Yeah.
Okay.
3D printed.
Are any of the edges or corners sharp?
No.
On that? Including the bottom ones?
Yeah, they're all bevel.
Okay, great. The second question is, I see your through tube on the top. It's not that the details on the bottom of it that's holding the tube from pulling through from the bottom?
Yeah, it's supposed to go all the way through, but as we were walking in, we like bumped it. It's now up just underneath there, but this tube should go all the way through.
So tomorrow we'll be sticking it.
Yes,
Yeah.
tomorrow we will be sticking
When we
it
have the paper clips and everything secured, it won't move when we bump it.
Yes.
Okay, great. I heard you say that it has a single B-cell battery in it?
That's
9
correct.
volt.
Oh, it's a 9 volt, yeah.
Sorry?
A lithium 9 volt battery, not you.
Lithium 9 volt display, yeah.
And is that enclosed, wrapped, foam, bouncing around?
We have it slightly wrapped.
Yeah, we have it, it's like, we have a little hole dug into the foam, Velcroed in, and then it's taped over, and I'm not worried about anything puncturing it because we just have seats in there. We don't have anything sharp. Obviously, for the previous team, that'd be an issue because they have a bunch of spinny, complicated stuff that could definitely harm the battery, but we have seats, so I think we'll be fine.
And it stayed put in its pocket?
Oh yeah, for sure. We actually, when we tried to, when you tried to change the battery, it was a significant effort to get it out.
Took a screwdriver and some effort to pry it apart.
So tomorrow, when it's time to fly, what do you need to do on the ground before we move out, and then what do you need to do specifically when we launch?
So as far as stuff before we launch, we just need to get the hand warmers, like shake them up, activate them, and put them in there. We're going to put Velcro on the back of them and also tape them just to be really sure that they stay in place. And then obviously we're going to tape up the top part with aluminum tape, tape up the sides, make sure it's real secure. And then we're good as far as that goes, other than turning it on, sending her up. And then when it comes down, we don't have any specific procedures that we need to happen. We just need to get the payload, and everything else is stuff we will do back at the
Power
school.
switches on the outside?
Yeah. Actually, switch it on, and it works. It should,
Okay.
yeah, there it goes. That would have been embarrassing if it didn't.
And one last question, what tool did you use to make these graphs?
Yeah, I made these graphs. So when it's storing the data, it stores it in just comma-separated like lines, lists basically. And so I just put it into Google Sheets, and it can make these graphs themselves. So you just take each column and tell Google to make a graph out of it, and it's actually very helpful, very quick.
I have one comment about switches on the outside. We had a team that we launched, and they had 2 switches they had to switch, and the payload was 1,000 feet in the air, and one student said to the other, "Did you turn it on?" And the other guy said, "No, I thought you did." So do you have a checklist before launch to turn those on?
We don't, but that's a great idea because actually we were really focused on that because if you look, we have a giant sticky note on the side that says "remove before flight" with 5 exclamation points because we have the quartz cuvette with tape over it, so we don't get any unwanted UV exposure before the experiment. I was like, it would be horrible if we forgot to remove the tape before flight, so we need that sticky note. And then we also have the SD card in it, and Miles here was like, okay, I need everybody to look at this and acknowledge that they saw me put the SD card in. So tomorrow morning, we're not like, did you put it in? I don't know, maybe. So we're going to make sure, thank you.
So actually, that comment you just made is important, and for everybody else. Typically speaking, SD cards do not stay seated, and so regardless of what type of SD card holder you have, whether it's the punch in or the flip down, you would be well advised to seat your card and then put some tape over it to make sure that it.
Thank you. Thank you. We have some extra tape. We'll do that.
And secondly, do you have tape or a panel to put over your switch so if it gets bumped, it doesn't get turned off?
Yeah, we could definitely put some tape over.
Okay. So tomorrow, I will ask you when we're walking on the flight line, I will ask you if you're ready to fly and if your light bulbs are all, or your LEDs are all colored there. We'll hear that question another time.
That's the last thing. We only have the one switch, and there is lights for it, so hopefully we shouldn't forget that.
Yeah, but a piece of tape over it, make sure that nobody is accidentally.
Put a piece of tape over it now in the off position, so it doesn't get bumped tonight.
Great thought,
and the
great thought,
batteries
thank
are
you.
dead in the
That would
morning.
also be a tragedy. All right, any other questions? Awesome, thank you guys.
Hello everybody, we're LQ, we're from the University of Colorado and Colorado Springs. This is Joshua and Nathaniel. My name is Alondra, and we are volunteers to finish this project. This was originally a senior design project at our school, and we just took it on and we wanted to fly, make sure it flies. So our mission objective is to transmit live video over L-band over frequency 1.243 gigahertz. Use off-the-shelf components, overlay telemetry data readings over the video, and storing backup of 10-second clips recording to the L-Cube. We discarded the continuous transmission for the duration of the flight and transmitting video while recording to the L-Cube. Our payload design is 3 battery packs in series, which will provide 10.5 amps or 8.4 volts to a voltage regulator, going to a 5 volt in powering the Raspberry Pi, and then from there the Raspberry Pi provides 3.3 volts to the sensors and 5.5 volts to the camera, and going to the USB 3.0, 5 volts to the software-defined radio that goes into these antennas that we see here. One for receiving, one for transmitting. Oh. Go back. Thank you very much. Transmission is at 1.243 gigahertz and receiving is at 1.241 gigahertz. Our ground stations will be from Josh's truck, the power inverter, charging his laptop, ground station laptop, going to his USB USRP transceiver, then to an SMA cable to Yagi antennas. The operations, so our sequence of powering the payload will turn on L-Cube and Wi-Fi router using Nathaniel's laptop and remote desktop. Log onto the L-Cube, start the system, bash script with sudo permission, start telemetry script, disconnect from remote desktop and power off Wi-Fi router. The ground station, he will just set up a ground station stationary until we lose signal.
Yeah, so that's going to change a little bit given the concept of operation you guys have up here. So what we're going to have to do now is we'll set up at the new rally point, which was in Lyman, it's Callahan. Yeah, so we'll set up in Callahan, try to receive our signal, and once we acquire, we'll track it as long as we can until signal burst. So yeah, the original plan was to launch from here and track it into the upper atmosphere, but now we'll have to go a little bit backwards. Sorry.
Here.
Okay.
I'm Nathaniel, undergrad at UCCS. This is our system of instructions that we have for our system bash script that we're using. We had to do it in this kind of form because we had some issues with how a video gets encoded and then pushed through a modulation. Because over time, as stuff was getting lost, we were getting a larger and larger delay. So we made it in the system. So we have 2 main operations. We have a GNU radio. It's a program for operating software-defined radios. And then we have an FFmpeg Linux tool that helps us with the video encoding. So the way that we have it set up currently is that we have to start our GNU radio transmission and then immediately start our FFmpeg encoding. And that puts it to a .ts stream, which we're doing over TCP server locally. And we have to get it at the exact rate. And the Raspberry Pi that we are currently using to do this loves to go faster, but we have to do a lot of things to make it slow down to where we need it to be, because it has to be just right. So we have this transmission going on for 3 minutes. This is about as good as we can get it before we start getting a heavy delay in the video. So we have this, so it does that, and then it kills the GNU radio software, and we switch over to reception mode. So in case of interference, we can actually send a termination command using BPSK modulation. And we kind of time it out so then we can find out when we stop getting the transmission, then we know that it's going into the receiving mode of it, and we send that code multiple times, and Then from that, it kills that reception, and it goes into a recording. So one of the issues we found was that we were trying to both record video to a file and also transmit the same video. Part of that problem made that where Raspberry Pi has to send something at a very specific speed, it made it kind of struggle with that a little bit. But we still do want the data back up from it. So we have it set up so it does 10-second increments in it, and then it closes it down, and it checks for a termination command. And so currently we have it set up so it gets out of that loop, and it goes into just a recording to a file. And that file we have reset every 5 minutes, just to make sure that if power goes off, it doesn't corrupt the whole file. It just corrupts one clip of the 5-minute increment. But if it doesn't receive the termination command, we go through the sequence again, and we can start receiving the transmission again. This is from our ground station operation. On the top side is our normal conditions for it. So we are also using Genie radio for the other side of it. And then we also have a terminal window. So Genie radio is outputting the .ts stream that we got before into a TCP server, which we can access on our laptop as well. We also have it set up so it's not only sending it to a TCP server, but it's also sending it to a file. So we're also logging all the transmissions that we receive from it. And then also in case of radio interference. So this is the cause of action that we have, and we have to down the line terminate it. So we wait for the end of the payload transmission that we can see from our waterfall graphs. Then we open up our kill command Genie radio script, and we execute it, and that will keep running the same command and keep bashing that terminate command over to it. And we also have our call sign right over here that we're using for our DVB-S to transmission.
Yeah, so for our testing regime, we did the usual tests. We did a drop test from 2 stories. We did a whip test. We performed a cold test and a stair pitch test. We just knocked down the stairs at school. We performed a 3-hour functionality test to make sure that we could continue to stay in the loop of sending video, stopping the video, switching to receive mode, waiting for a kill command, and continuing that loop. We did multiple image capture tests, shutdown command test, and we also performed long-range testing. Slide. All right, yeah, so the results for our whip test, minimal damage with the whip test. The paper clip pins were bent, but they stayed and held. Slide. The drop test. The drop testing was successful. We basically just dinged up the corners of the thing. The aluminum tape split somewhat, but we also have this thing reinforced with lots and lots of hot glue to make sure that even if the tape goes, we have a backup adhesion. Go. Thank you. Stair pitch test, slight damage, nothing to report on the stair test. Slide. A table test in the lab, we ran it for 3 hours. We ran the flight capture and saved all those images to file on the computer as well as on the satellite. And we tested our shutdown command in the lab. Back a couple. There we go. Yeah, we performed a long-range test from the balcony at Pikes Peak State College all the way over to the University of Colorado Springs parking garage. The results of that particular test were inconclusive. We had a lot of noise in the environment on 1.2, and we also had a lot of ground clutter. So DVB-S2, which we're using, is not at all designed to handle ground interference. It's designed for the satellite direct, perfect line of sight only. DVB-T is what we'd use if we were ground-based. So we weren't able to get high enough to make our signal work that far out, but we were able to make it work at closer range with better lines of sight. System integration, who's doing systems? Yeah.
Honestly, until recently, telemetry was not going to be something that we had in our mindset. We were mostly focused on our transmission of video. It wasn't until the last week when we started getting all these sensors up and working and good to go. So we have, this is our new, it looks like a mess right here, but we're all using just I2C connection protocoling. So in the end result, it's just all the wires connected together. But we're running 3 sensors on it. We're getting pressure, humidity, gyroscopic sensors, and pressure sensors to get altitude. And with that, we are overlaying some of our sensor data onto our transmission of the video. So while it is flying, we're actually able to get the altitude readings and the internal temperature readings. This is our payload. We have our switch visible on that side, which we will get tape now for the launch. We have our team name and contact info visible with American flag. And we have washer glued down on the top and the bottom. And then all that's left to go for launch is putting the pin on the bottom and putting a little bit more tape. Yes, this is wire secured. There's a lot of wires. We had to use a lot of hot glue. And to be honest, we are a little bit heavier, so we are re-weighing it after this meeting. And then this is our weight summary. So we came out at 881 grams currently, but we may have added a little bit of weight. So we're definitely rechecking it to make sure we're underneath the kilogram weight. And this is a picture of our previous team that had done this experiment. This is the video that they captured from it, but they were just storing it directly to a data file, and this is what we're hoping to see on our end.
I have a question as to your power output and what are you using for your transmit antenna and your receive antenna?
Yeah, so for the transmit antennas, we're using dual circular polarized wire antennas. We're transmitting at about, we see 1.2 watts. You said 1.2 watts?
I think it's
what you're putting out? 1.6? Yeah, so it's 1.6 watts is what we're outputting on these circularly polarized antennas.
Okay.
And then is, yeah.
What's the orientation? Where are the antennas though?
They're on both sides of the unit. So we have one on this side and one on this side.
So you're going to get a pattern this way?
We were wondering about that. But we did a lot of our testing where it was tilted like that because these are typically used for drone operation. And so the only direction that we could really not get the signal was if it was directly behind the antenna where the SMA connection was. But other than that, we were able to, we did our long range testing with.
You have tested the pattern of the payload transmission.
How long was your long range testing?
So our longest range test was, 5 miles. And our most successful long range test was about a mile. But that was including interference and interference and ground clutter. So those kind of impacted our communications pretty significantly. And then as far as receive goes, we are using a pair of 17.2 dB Yagi antennas that are for 1.2 gigahertz, and those are plugged into an Edis Research at software-defined radio. And one of those antennas is actually our transmit antenna for running our kill command.
Do you have a way to automatically point your antennas?
No.
A couple of questions. You addressed the power switch. So those switches have a tendency, even when you tape them, when you just tape the on piece down, you want to be careful so you not look at something that's a little bit of a shield over the top of the bottle cap, top of the wall or something like that, so that you can The second comment would be, or question would be, talk to me about your battery. There's a lot of power flying out of there. I want to understand how you're going to keep them safe.
Yes, so we do have some foam in, so we have 3 packs of 2 cells, and each of those have foam and then wrapped in, and then wrapped in electrical tape, and then we have them hot glued down to the bottom. And when the whip testing was done, it was done with the batteries in them.
Do those cells have BMSs in each cell?
The buck converters.
Safety order, a little, look like a nickel on the end that has what's the overcurrent, undercurrent, overcharge, undercharge, that kind of stuff.
I'm not quite, honestly, well, so this part was done by our previous team. So when they did like cold testing with the batteries and the whip testing, that was with the previous team.
And so you inherit these batteries kind of as is?
Yes, they helped us charge it and get it up to what it should be and everything. And when we were testing it, we had them sitting for a little bit, but they were all working. When we did our 3-hour test, that was before even charging it with what they had on it before.
So can we go back to the one line of the power system and walk through that in case? So we have 3 of those packs that you showed me a picture of. They're wired directly in parallel, no diodes or fusing or anything. They're just electric packs, wires come together and it goes into the new regulator.
Yes.
Okay. How certain are you that those batteries aren't going to move around inside the enclosure?
We're pretty certain. A lot of the tests, the whip test, the stair test, that was all done with the batteries in it. And we made sure to, we redid the hot glue on it and everything, and we made sure that it was seated pretty well into it.